Our next talk is by Shijin Duan, and the topic is a brain-inspired low-dimensional computing classifier for inference on tiny devices. And the presenter is from Northeastern University.
Hello everyone, my name is Shijin. Apologize that I didn't get to the symposium on the ground. I will talk about our work, which is a brain-inspired low-dimensional computing classifier for inference on tiny devices. The story will start from the edge devices, which are not capable of complex machine learning algorithms, and especially for the tiny devices. The severe resource limitation makes the machine learning algorithms much more challenging. And as a recent promising solution, the hyperdimensional computing is raised as a machine learning framework for implementation on the resource-constrained devices. As shown on the right, by randomly sampling in a high-dimensional space, the HDC can project an attribute or its value to a high-dimensional vector called hypervectors. For a machine learning dataset, the attributes are just features or pixels. And in this work, we focus on the binary HDC for the sake of hardware efficiency. So for the hypervectors in the binary HDC, they are either 1 or -1 in bipolar system or 0 or 1 in a binary system. And with the hypervectors representing attributes and values, they are bound in a cascaded manner to generate a sample vector representing the entire object. Now let's take a brief glance at the HDC. First, we need to generate the feature and value vectors, value hypervectors, so that we can map an input to a high-dimensional space. We assume an input has n features and m discretized feature vectors. For example, the mNeast samples has 74 pixels and 256 pixel values. And during the feature hypervector generation, the feature hypervector is randomly sampled from a large dimensional space, and two feature hypervectors are orthogonal to each other. That's to say, the normalized Hamming distance between any two feature hypervectors are about 0.5. And for the value hypervector generation, the hypervectors are consecutively distributed to obey the correlation between the values. Generally, the Hamming distance between two value hypervectors are proportional to the distance between the values they represent, and it's close to a linear relation. So the generated feature and value hypervectors are stored in the item memory, the IM in this figure. During the encoding, the feature hypervectors and the corresponding value hypervectors are bound using the bitwise multiplication, and they are added up to represent the input sample. The sign function is applied for the binary HDC. For the training phase, all the sample hypervectors in a certain class are collected, and they are added up to represent the corresponding class. Also, binarization is used. The derived binary class hypervectors are stored in the associative memory, the AM in this figure. When an input image is for inference, it's first encoded as a binary hypervector and then compared with all the class hypervectors. The class with the lowest Hamming distance with that hypervector is marked as the predicted label. Another important observation is that for two binary vectors, their Hamming distance and cosine similarity are equivalent. I will skip this derivation due to the time limitation. But the conclusion is, in this way, the predicted label can also be determined by the dot product. And this conclusion is quite important for our work to map the HDC model to an equivalent neural network. So after reviewing the HDC, we can find that the binary HDC suffers from two drawbacks. First, the dimension of the hypervectors must be high to ensure the randomness and the orthogonality. But it will lead to large model size and a huge number of parallel operations. And tiny devices will not be happy with this. And second, as reported in previous works, the low inference accuracy on the many tasks prevents its application on the realistic scenarios. So this is our motivation that we seek for a new way to rethink of the binary HDC so that it can be presented as a low-dimensional model but has improved prediction accuracy. And now let's review the HDC steps one by one from a totally new perspective. First is the value mapping. I mean, how to generate the value hypervectors. We denote the value representation as a gadget called ValueBox. And it will map one input value as a binary or bipolar vector following a certain rule. Except for the standard HDC rule, we introduced two other manual rules. The fixed point rule is to use the naive binary code of the input value, like 9 can be 1001, and the thermometer rule is to quantize the input value into a thermometer format. And for example, 9 will be represented as 0111 in this case. And in our LDC design, we take advantage of the strong representing power of the neural network and use a trainable neural network for the value box rather than a manual design. And then the generated value vectors will be bound with feature vectors as the final output sample vector of this encoding process. So the normal HDC work requires the dimension of value and feature hypervectors are equal, but our LDC design only requires one is multiplies of the other one. That's to say, the value vector can be duplicated by n times when doing the encoding with the feature hypervectors to align the dimension. For example, for the S feature, the element-wise multiplication can be computed separately as n parts. And in each part, the element-wise multiplication is equivalent to the diagonal matrix of the feature vector times the value vector, and as a matrix multiplication. So the encoding now becomes an n-part matrix multiplication in a parallel, as I showed in this figure. And these small diagonal matrices can compose a large sparse matrix. And the input value vectors are also stacked as a long binary vector. And in this case, this element-wise binding is actually a linear layer in the neural network format, while the sign function is the activation. And now that we have the sample hypervector as the output of the encoding, we can do the inference now. Because the cosine similarity and the Hem distance are equivalent to each other, the similarity checking is equivalent to the matrix multiplication, which can also be mapped to the operation in a binary neural network. So by integrating different stages of the LDC classification, we construct an end-to-end neural networks showing in this figure. Here, the value mapping layer is non-binary, while the feature and class layer are binary neural networks. With both binary and non-binary weights, this framework realized the same function as the normal HDC model. This is the design flow of our classifier. So please note that a single value box here is shared by all the features. And in order to train an LDC model, we can jointly train the ValueBox network together with this subsequent binary networks. And below is the training configuration we use for the LDC classifier, which is also the state-of-the-art BNN training method. And as for the inference, we need to extract all the needed vectors. For the value vectors, we record the outputs corresponding to each possible inputs. For example, the MNIST dataset has 256 possible values corresponding to 256 specific value vectors. And for the feature and class vectors, we just extract the non-zero weights in the feature and class layer, respectively. And in this way, we project the HDC model to an equivalent neural network structure and propose a principal training strategy to train the model. So we don't need to randomly generate the feature and value vectors anymore, but we train them. For the experimental validation, we select 5 common datasets on the HDC models, and the platform we used for the evaluation is shown below. First, we validate the effectiveness of our neural network shaped value box. And the result shows that the neural network structure can discover better value boxes than the manual designs to achieve higher accuracy. But on the other hand, it has no significant differences by varying the network size. And then we explore the dimension selection on the feature and value hypervectors. And the dimension can be as small as tens or hundreds, rather than as large as 10,000 in previous HDC work. The results show that, in general, a higher value vector dimension yields a higher accuracy, simply because it takes more dimension, it takes more information. However, even the dimension of value vector is small, like 2 or 4, we can also achieve a reasonably high accuracy when increasing the dimension of feature vectors. Now let's come to the important part. We evaluate the inference accuracy that the HDC can achieve compared to both the basic and state-of-the-art HDC models. The result shows that the LDC can outperform existing HDC models, and for the state-of-the-art HDC, the hypervector dimension must be as large as 8,000 to prevent the accuracy reduction. By contrast, our LDC classifier reduced the dimension significantly to tens without introducing any extra cost during the inference. Further, another evaluation for the LDC classifiers is the robustness against the bit errors. Specifically, we inject bit errors in the associated memory. Is just the class vectors. So with different bit error rates, and then observe the inference accuracy. As we can see, our LDC classifier has the highest accuracy and also achieves comparable robustness with the normal HDC models. For the hardware implementation, we designed a pipeline structure for the feature encoding, and rather than in parallel, to fit in tiny devices. And each time we only compute encoding for one feature, so only one vector multiplication block and several the blockrams are required. And because of the low dimension, the latency of this pipeline encoding is still on a microsecond scale. And subsequently, one adder is utilized to accumulate the multiplied vectors, and the non-binary result is binarized using a comparator with a certain threshold. And for checking the similarity, we also use a pipeline structure, and then a tree adder along the vector dimension is used for the Hamming distance calculation. And we show the efficiency of our LDC hardware in the table below. Generally, it has quite low model size, and also the low dimension can benefit the resource utilization and execution time. For the energy consumption, the result shows that our LDC classifier is the lowest one. It's simply because the very low resource utilization and short latency. So as a conclusion, we address the fundamental drawbacks of existing HDC models and propose an LDC alternative with quite low dimensions. And evaluation results highlight that the LDC has overwhelming advantages, which is particularly suitable for the inference on the tiny devices. Okay, thank you. This is a brief introduction of our work. I'll be glad to answer any questions.
Questions for Shijin?
Yeah, I'm Laura Galindez from UC Berkeley. So I was just wondering if you considered using Hamming distance or cosine similarity in your loss function that you used to actually learn the neural network.
Yes, so for the, because this paper is talking about the binary HDC. So for the binary, the Hamming distance is equivalent to the cosine similarity. And let's say in general, let's say a non-binary HDC, the cosine similarity is also used. So so it's the cosine similarity is a feasible solution for the HDC problem, and for sure you can use the Hamming distance, but they are just equivalent to build the neural network.
Okay, thank you.
And we are very thankful for our sponsors. The premier sponsor this year is Edge Impulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, Pixart, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.